1885. An Ohio steel rolling works where steam hissed through massive iron pipes and hammers rang against red-hot metal. The engineering consensus from European boiler makers was crystal clear. The future belonged to thin steel walls, welded seams, and pressures pushing 300 pounds per square inch. Lighter, faster, more efficient. Then plant engineer John Carson stepped forward with a proposal that made visiting consultants shake their heads in disbelief. 1-inch thick wrought iron plates, hand-driven rivets 3/4 of an inch in diameter. Operating pressure kept to just 120 pounds per square inch. Everything the Europeans called backwards, outdated, impossibly heavy. A 50-ton monster when modern boilers weighed just 8 tons. The consultants warned it would never compete with sleek European designs, but Carson's thick-walled, overbuilt American boiler would prove something that shattered every assumption about modern engineering. Sometimes the heaviest path leads to the longest journey. Carson stood in the drafting room of the Mahoning Valley Steel Works that October morning, his calloused fingers tracing the dimensions across blueprints that most engineers would have dismissed as impossibly conservative. The numbers told a story that flew in the face of everything the industry's leading voices were preaching. While European manufacturers boasted of their latest innovations, welded steel shells weighing mere tons, operating at pressures that would have terrified engineers just a decade earlier, Carson's proposal called for something entirely different. 1-inch thick wrought iron plates, riveted joints with 3/4-inch diameter fasteners, a working pressure of 120 pounds per square inch when competitors were pushing toward 300. The contrast wasn't lost on Dr. Frederick von Hoffmann, who had arrived from New York that morning with a leather portfolio filled with testimonials from German steelworks and British boiler manufacturers. Von Hoffmann adjusted his wire-rimmed spectacles as he studied Carson's drawings, his educated accent cutting through the ambient noise of the mill. Herr Carson, you must understand that the future of steam generation lies in efficiency. Weight reduction, pressure optimization. These specifications, he tapped the blueprint with a manicured finger, represent thinking from the 1860s. Carson had heard variations of this argument from consulting engineers who traveled the circuit between Boston, Philadelphia, and New York, carrying with them the latest European theories on pressure vessel design. They spoke of hoop stress calculations and metallurgical advances that promised boilers lighter, faster, and more economical than anything American foundries had produced. The mathematics seemed irrefutable. A modern welded boiler could deliver the same steam output as Carson's proposed design while weighing 60% less and occupying half the floor space. But Carson had walked through enough mill floors to know what those elegant calculations missed. He had seen the aftermath of seam failures in thin-walled vessels, witnessed the cascading shutdowns that occurred when sophisticated European designs met the harsh realities of American industrial water supplies and round-the-clock operation schedules. The immigrant workers who operated these machines, Polish riveters, German plate fitters, Irish inspectors, understood something that boardroom consultants often overlooked. Durability mattered more than efficiency when your livelihood depended on continuous operation. Samuel Green, owner of the adjacent cotton mill, had agreed to fund Carson's experimental boiler shop precisely because he had grown tired of replacement cycles. His current steam plant, assembled from a mix of British and German components, required major overhauls every 15 years and complete replacement every 2 decades. The costs weren't just monetary. They included lost production, displaced workers, and the constant anxiety of operating equipment at the margins of its design life. When Carson proposed building boilers that might operate for 50 years or more, Green saw an investment that could transform his entire business model. The technical challenges became apparent as soon as construction began. Wrought iron plates measuring 8 feet in width and 1 inch in thickness cost 30% more than the thinner steel alternatives that most manufacturers were adopting. The rolling process alone required specialized equipment and experienced operators who understood how to work the material without introducing stress concentrations or surface defects. Each plate had to be heated, shaped, and cooled using techniques that dated back to the early days of steam engineering, but demanded a level of precision that few shops could maintain. Finding skilled riveters proved even more difficult. The men who could drive 1-inch diameter iron rivets through double lap joints were mostly immigrants who had learned their trade in shipyards or locomotive works. They commanded higher wages than welders and worked at a pace that seemed glacial compared to modern assembly methods. Each rivet required individual heating in a forge, precise placement through pre-drilled holes, and hammering that compressed the metal into a joint stronger than the surrounding plate material. The process was labor-intensive, time-consuming, and utterly dependent on human skill rather than mechanical automation. Von Hoffman visited the construction site regularly, documenting what he clearly viewed as an exercise in industrial nostalgia. His reports to potential clients emphasized the inefficiencies, the months required to complete a single boiler shell, the workforce of immigrant craftsmen who communicated in a mixture of English, German, and Polish, the massive overhead cranes needed to position plates that weighed tons rather than hundreds of pounds. He calculated that Carson's approach required nearly double the man-hours of comparable European methods, while producing equipment that occupied significantly more space and generated steam at lower pressures. The criticism stung because it contained elements of truth. Carson's boiler shop employed 120 workers when modern facilities accomplish similar output with half that number. The riveting process alone required 20 specialists who heated, positioned, and secured 10,000 individual fasteners for each boiler shell. Plate fitting operations took weeks rather than days, with teams of workers using hammers, tongs, and measuring instruments to ensure that joints aligned with tolerances measured in 64ths of an inch. As winter approached, Carson found himself standing beside the half-assembled boiler shell in the growing darkness of an Ohio evening. The massive iron structure rose before him like the skeleton of some industrial cathedral, its dark plates joined by rivets that glowed dull red in the forge light. Steam from the heated rivets created shifting patterns in the cold air, and the rhythmic hammering of the assembly crews provided a percussion that echoed off the shop walls. The conventional wisdom suggested that this approach was doomed. European consultants had the backing of advanced metallurgy, proven stress analysis, and cost calculations that demonstrated the superiority of their methods. The American steel industry was already moving toward thinner materials, welded construction, and higher operating pressures. Carson's heavy-duty design seemed to represent a step backward into an era of over-engineering that modern efficiency demanded they abandon. But looking at the solid mass of iron and steel taking shape before him, Carson suspected that the conventional wisdom might be missing something crucial. The question that would define the next decade wasn't whether his approach could compete with European methods on paper. It was whether it could survive the test of time in ways that elegant calculations couldn't predict. The construction details that emerged through the winter of 1885 revealed the true scope of Carson's engineering philosophy. The boiler shell itself measured 8 feet in diameter and stretched 16 feet in length, dimensions that required a foundation of reinforced brick and steel capable of supporting nearly 50 tons of iron, water, and steam. Each wrought iron plate arrived from the rolling mill as a massive rectangle measuring 8 feet by 12 feet, its surface bearing the distinctive grain patterns that marked genuine wrought iron rather than the newer steel alternatives that most manufacturers were adopting. Johnny Martinez, the head riveter, understood better than anyone why Carson had insisted on 1-inch plate thickness. As he guided his crew through the process of fitting the first shell sections, he explained to younger workers how the extra material would behave under the thermal stresses of daily heating and cooling cycles. The thick walls provided what engineers called corrosion allowance, extra metal that could rust away over decades without compromising the vessel's structural integrity. Where modern boilers operated with safety margins measured in 1/16 of inches, Carson's design incorporated quarter-inch buffers against the inevitable deterioration that came with industrial service. The riveting process itself represented a craft that was rapidly disappearing from American industry. Each of the 10,000 iron rivets required for a single boiler shell began as a rod of wrought iron that had to be heated in a coal forge to exactly the right temperature, hot enough to deform under the hammer blows that would expand it into a tight joint, but not so hot that the metal became brittle or difficult to work. Martinez and his crew had developed a rhythm that allowed them to heat, position, and drive approximately 200 rivets per day, working in teams of 4 men who moved with the precision of a military drill unit. Mary O'Neill, the Irish-American plate fitter who served as the shop's unofficial quality inspector, brought a level of measurement precision that surprised visiting consultants. Using micrometers calibrated to thousandths of an inch, she verified that every rivet hole aligned perfectly with its counterpart in the adjoining plate. The double lap joint design that Carson had specified required this accuracy. Any misalignment would create stress concentrations that could lead to joint failure under pressure. O'Neill's meticulous approach meant that plate fitting operations often took twice as long as comparable work in other shops, but the results justified the extra time. The fire tube design represented another departure from modern practice. Where contemporary boilers used sophisticated water tube arrangements that maximized heat transfer efficiency, Carson's system employed hundreds of 2-inch iron tubes that carried hot combustion gases through a shell filled with water. The arrangement echoed the locomotive practice of the 1870s, prioritizing reliability and ease of maintenance over thermodynamic optimization. Each tube was individually rolled, fitted, and secured with expansion joints that allowed for thermal growth without creating dangerous stresses. What made Carson's approach revolutionary wasn't the individual components. Wrought iron, riveted construction, and fire tube heat exchange were all established technologies. The innovation lay in how these elements work together to address the fundamental challenge of industrial steam generation, continuous operation under harsh conditions with minimal maintenance. The thick walls provided generous corrosion allowances. The riveted joints flexed under thermal expansion rather than cracking like welded seams. The wrought iron material resisted the localized pitting that often initiated catastrophic failures in steel vessels. Even the untreated feed water that most engineers viewed as a liability became an asset in Carson's design. The mineral deposits that accumulated inside the shell, scale formations that reduced heat transfer efficiency, actually created a protective barrier between the raw water and the iron surfaces. This natural scale layer, built up over months of operation, provided additional corrosion resistance that sophisticated water treatment systems couldn't match. The thick walls meant that even significant scale buildup didn't compromise the vessel's pressure-containing capability. Von Hoffmann documented these construction methods with growing bewilderment. His calculations showed that Carson's approach required nearly 4 times the material cost of equivalent European designs, while the labor requirements stretched construction timelines from weeks to months. A single shell required 4 separate batches of plate rolling, each taking 4 weeks to complete as the mill worked the wrought iron to Carson's exacting specifications. The riveting operations alone consumed nearly 3 months, with Martinez's crew working systematically from one end of the shell to the other, sealing each joint with lead caulking that would remain tight for decades. The breakthrough moment arrived on a gray March morning in 1886, after 6 months of construction that had tested the patience of everyone involved. The completed boiler stood in the center of the mill like a monument to American industrial ambition, its dark iron surfaces reflecting the overhead lights, steam connections sealed and ready, firebox loaded with coal from the Pennsylvania fields that would provide its first test. Samuel Green stood beside Carson as the lighting crew ignited the fire that would begin the most crucial phase of the entire project. The initial pressure test began conservatively, with steam building slowly toward 60 pounds per square inch, while Carson monitored every joint, every connection, every surface for signs of leakage or distress. The massive shell remained absolutely tight, its riveted seams showing no evidence of the weeping that often marked new construction. As pressure climbed toward the design target of 120 pounds per square inch, both men felt the tension of months of work and investment coming to focus on this single test. When the pressure gauge finally stabilized at 120 pounds per square inch and held steady for 72 hours without requiring additional steam input, Carson and Green exchanged a nod that carried the weight of vindication. The American approach, heavy, expensive, labor-intensive, and thoroughly unfashionable, had produced exactly what Carson had promised: a steam generator that operated at its design pressure without stress, without leakage, and with the kind of structural margin that suggested decades of reliable service ahead. Von Hoffman's final report acknowledged the test results while maintaining his skepticism about the broader implications. The boiler worked, certainly, but at costs that made it economically impractical for widespread adoption. The American method might satisfy the particular requirements of one Ohio mill, but it could never compete with the efficiency and economy of modern European practice. Time would prove whether Carson's triumph represented genuine innovation or simply an expensive exercise in industrial nostalgia. Success bred ambition, and by the spring of 1887, Carson had convinced Green to expand the boiler shop into full-scale production. The single prototype that had proven itself through months of continuous operation would serve as the template for 9 additional units, each built to identical specifications and designed to power Green's growing cotton mill operation. The expansion required doubling the workforce and establishing supply contracts with Pennsylvania iron producers who could deliver the massive quantities of wrought iron plate that Carson's design demanded. The production process that emerged over the next 2 years transformed the Mahoning Valley Works into something resembling a precision manufacturing operation scaled to handle components that weighed tons rather than pounds. Martinez's riveting crews developed standardized procedures that allowed them to complete a shell in 10 weeks rather than the original 12, while O'Neill's inspection protocols ensured that each boiler met tolerances that exceeded anything required by existing safety codes. The 10 boilers that emerged from this production campaign represented more than individual steam generators. They constituted a practical test of whether American heavy-duty engineering could compete with the efficiency-focused European approach on an industrial scale. The cotton mill that these boilers powered operated under conditions that would have challenged any steam plant. 24 hours per day, 7 days per week, the facility demanded continuous steam for spinning machinery, heating systems, and power generation. The boilers cycled through heating and cooling phases that created thermal stresses far more severe than the steady-state conditions that most engineering calculations assumed. Green's operation processed raw cotton into finished textile products using machinery that required precise steam pressures and temperatures, variations that could affect product quality and production rates. 5 years into operation, the first comprehensive inspection revealed results that surprised even Carson. Using the same measurement techniques that O'Neill had employed during construction, inspectors found that the boiler shells retained an average wall thickness of 9/10 of an inch, a loss of only 1/10 of an inch from the original 1-inch specification. The riveted joints showed no signs of loosening or leakage, while the fire tubes remained clear of the deposits that often reduced heat transfer efficiency in competitor installations. Most remarkably, the natural scale formation that had built up on interior surfaces appeared to have stabilized into a protective layer that actually enhanced corrosion resistance. These inspection results took on greater significance as reports filtered in from other industrial facilities in Ohio, Pennsylvania, and New York. Mills that had installed modern welded boilers during the same time period were experiencing failures that ranged from minor leakage to complete seam separations. The thin-walled designs that European consultants had promoted as the future of steam generation were proving vulnerable to the cyclic stresses and water quality issues that characterized American industrial operations. Replacement cycles that had been projected at 25 to 30 years were being revised downward to 18 to 20 years, with some installations requiring major overhauls within 15 years of commissioning. By 1892, Green's expansion plans required additional steam capacity, and Carson found himself in the enviable position of pointing out that his original boilers were operating at performance levels that exceeded their design specifications. Pressure tests conducted during routine maintenance showed that the shells could safely handle 150 pounds per square inch, 25% above their rated capacity, while maintaining the structural margins that had been built into the original design. The thick walls that had been criticized as wasteful over-engineering were proving their value as insurance against the unpredictable stresses of continuous industrial service. The peak moment of vindication arrived during a trade association meeting in Cleveland, where mill owners gathered to discuss the growing problem of boiler maintenance and replacement costs. Green stood before an audience of his peers, and delivered a presentation that used Carson's boilers as a case study in long-term capital planning. While competitor facilities were budgeting for major steam plant overhauls, Green's operation was projecting another 40 years of service from equipment that had been in continuous use for nearly a decade. The numbers Green presented challenged fundamental assumptions about industrial equipment life cycles. His boilers had cost approximately twice as much per unit as comparable European designs, but their operating costs were proving to be significantly lower. Maintenance requirements were minimal. Annual inspections, periodic rivet tightening, and routine cleaning of fire tubes. No major component replacements had been necessary, and the structural condition of the vessels suggested that none would be required for decades to come. Most importantly, the plant had experienced zero unscheduled downtime due to boiler failures, a reliability record that translated directly into production efficiency and worker employment stability. Carson used these results to develop what became known as the Mahoning Valley method, an engineering approach that prioritized long-term durability over short-term efficiency metrics. The philosophy extended beyond boiler design to encompass material selection, construction techniques, and maintenance protocols that assumed equipment would operate for 50 years or more. While European manufacturers continued to focus on weight reduction and pressure optimization, Carson's method emphasized generous safety margins, proven materials, and construction quality that could withstand decades of industrial service without major intervention. The success of Green's mill attracted attention from industrial facilities throughout the Midwest, and Carson found himself consulting on steam plant designs from Michigan to Tennessee. Each installation provided additional data points that reinforced the central thesis of his approach, that American industrial conditions demanded engineering solutions that could survive harsh operating environments for extended periods. The thick-walled, riveted boilers that had once seemed like expensive anachronisms were proving to be precisely what American industry needed to achieve the combination of reliability, longevity, and operational flexibility that competitive manufacturing required. Von Hoffman, observing these developments from his New York office, began to revise his assessment of American engineering practices. While he maintained that European methods remained superior for applications that prioritized efficiency and cost minimization, he acknowledged that Carson's approach addressed operational realities that purely theoretical calculations often overlooked. The American method might be heavy and expensive, but it was also proving to be remarkably durable in ways that sophisticated stress analysis had failed to predict. The crisis that would define Carson's legacy began with what seemed like a reasonable business decision in the spring of 1895. Green's cotton mill had grown beyond the capacity that even 10 heavy-duty boilers could provide, and competitive pressures demanded higher steam pressures to drive the sophisticated new textile machinery arriving from Massachusetts factories. European manufacturers had perfected welded boiler designs that could operate safely at 200 pounds per square inch, while occupying half the floor space of Carson's riveted units. The mathematics were compelling. A single modern boiler could replace 2 of Carson's heavy-walled units, while reducing fuel consumption and maintenance requirements. Von Hoffman returned to the Mahoning Valley that summer with blueprints for a state-of-the-art pressure vessel manufactured by Krupp Industries in Germany. The design represented everything that Carson's approach was not: thin steel walls measuring 3/8 of an inch, welded seams that eliminated thousands of potential leak points, and operating pressures that would have terrified engineers a decade earlier. The unit weighed less than 8 tons compared to the 50-ton monsters that Carson had built, yet it promised to deliver equivalent steam output with significantly improved fuel efficiency. Green, facing pressure from textile buyers who demanded lower production costs, authorized the purchase despite Carson's reservations. The installation process revealed immediate differences in construction philosophy. Where Carson's boilers required foundations capable of supporting massive structural loads, the European unit needed only a steel framework and concrete pad. The welded shell arrived by rail from the East Coast already assembled, requiring just 2 weeks to install compared to the months that Carson's riveted construction demanded. The fire tube bundle consisted of high-grade steel tubes arranged in patterns optimized for heat transfer efficiency. while automatic feed water controls promised to maintain water quality within specifications that would prevent the scale buildup that Carson's design actually relied upon for corrosion protection. Initial operation exceeded expectations. The German boiler reached its rated pressure of 200 pounds per square inch smoothly and maintained stable output throughout the demanding production cycles that characterized Green's 24-hour operation schedule. Fuel consumption dropped by nearly 15% compared to Carson's units, while the compact design freed up valuable floor space for additional textile machinery. Von Hoffmann's calculations appeared vindicated. Modern engineering had produced a steam generator that surpassed American heavy-duty construction in every measurable parameter. The first signs of trouble emerged during the second year of operation, when routine inspections revealed hairline cracks developing along the longitudinal weld seams that joined the cylindrical shell sections. The cracks appeared to result from thermal cycling, repeated heating and cooling that created stresses at the transition zones between welded and base metal. European operating manuals had specified water treatment protocols designed to prevent the mineral accumulation that could accelerate corrosion, but Green's facility lacked the sophisticated chemical treatment systems that German mills employed as standard practice. The raw water from Ohio wells contained dissolved minerals that gradually built up deposits in ways that European engineers hadn't anticipated. Carson examined the developing cracks with growing concern, recognizing stress patterns that his riveted joints would have accommodated through elastic deformation. Welded seams, while initially stronger than mechanical fasteners, had no capacity to flex under thermal expansion. Each heating cycle created microscopic separations along the fusion zone, and these tiny failures accumulated over time into visible cracks that compromised the pressure boundary. The thin wall thickness that made the European design so efficient also meant that any corrosion or cracking quickly approached critical dimensions. The catastrophic failure occurred during a routine production shift in March of 1898, nearly 3 years after installation. A longitudinal seam crack that had been monitored for months suddenly propagated along 6 feet of the shell's circumference, creating a steam release that filled the boiler room with superheated vapor and forced immediate evacuation of the entire mill complex. While no workers were seriously injured, the sudden loss of steam pressure shut down all textile production for 48 hours while emergency repairs were attempted. The financial impact extended beyond lost production. Green faced penalty payments to customers whose orders couldn't be completed on schedule, while the workforce lost 2 days of wages during a period when alternative employment was scarce. Emergency inspection of the failed unit revealed the full scope of the problem. The original crack had initiated at a point where feed water chemistry had created localized corrosion, concentrating stress at exactly the location where the welded joint was most vulnerable. The thin wall section that remained intact measured barely 1/4 inch, well below the minimum thickness required for safe operation at design pressure. Most disturbingly, similar crack development was evident at other weld locations throughout the shell, suggesting that the entire vessel had reached the end of its safe operating life after less than 3 years of service. The failure's impact extended beyond Green's facility when inspections at neighboring mills revealed similar deterioration in other European manufactured boilers installed during the same period. The promised 25-year service life was being revised downward to 12 to 15 years, with some installations requiring major repairs within a decade of commissioning. The cost advantages that had justified the original investment evaporated when life cycle expenses included premature replacement and the productivity losses associated with unplanned shutdowns. Meanwhile, Carson's original boilers continued operating without interruption. Daily inspections showed no evidence of the stress cracking that had destroyed the German unit, while ultrasonic thickness measurements confirmed that wall dimensions remained well within safe operating limits. The riveted joints that had been criticized as primitive technology were proving their ability to accommodate thermal stresses without catastrophic failure. Most remarkably, the natural scale formation that had been viewed as an operational liability was providing corrosion protection that expensive water treatment systems couldn't match. The crisis forced a fundamental reassessment of engineering assumptions that had guided American industrial development through the 1890s. Carson found himself questioning whether even his conservative approach provided adequate safety margins for the demanding conditions that characterized American manufacturing. The European failure had demonstrated that sophisticated engineering could produce equipment that appeared superior while containing hidden vulnerabilities that emerged only under long-term operational stress. The challenge for American industry was developing design philosophies that could survive not just initial testing, but decades of continuous service under conditions that laboratory analysis couldn't fully predict. The failure of Green's European boiler created an opportunity that Carson seized with the methodical precision that had characterized his original design philosophy. Rather than abandon the heavy-duty approach that had served the mill reliably for over a decade, he proposed a comprehensive upgrade program that would incorporate lessons learned from both his successes and the recent catastrophe. The redesign process that emerged through the summer of 1898 combined Carson's conservative engineering principles with targeted improvements that addressed the operational realities revealed by 15 years of continuous industrial service. Carson's enhanced specifications maintained the fundamental elements that had proven successful: 1-inch wrought iron walls, riveted construction, and generous safety margins, while incorporating refinements that reflected deeper understanding of long-term performance requirements. The maximum operating pressure remained fixed at 150 pounds per square inch, a conscious decision to prioritize longevity over the higher pressures that competitors were pursuing. This pressure ceiling provided structural margins that could accommodate decades of thermal cycling, corrosion, and the inevitable material deterioration that occurred in any industrial environment. The most significant innovation involved water treatment protocols that struck a careful balance between preventing harmful deposits and preserving the beneficial scale formation that had contributed to corrosion resistance in the original installations. Carson worked with O'Neill to develop filtration systems that removed abrasive sediments and dissolved metals while allowing the mineral content that created protective interior coatings to remain in the feed water. The approach required none of the sophisticated chemical treatment systems that European designs demanded, instead relying on mechanical filtration and settling tanks that mill workers could maintain using existing skills and equipment. Scheduled inspection procedures represented another departure from previous practice. Where earlier maintenance had been largely reactive, responding to problems as they developed, Carson instituted quarterly thickness measurements and annual rivet inspections that would detect deterioration before it reached critical levels. O'Neill trained a cadre of mill workers in the use of ultrasonic measurement devices that could assess wall thickness without requiring boiler shutdown, while Martinez developed procedures for retightening rivets that had loosened through decades of thermal expansion and contraction. The enhanced boiler design that emerged from this process incorporated structural details that reflected 30 years of operational experience. Rivet patterns were optimized to distribute stress more evenly across joint areas, while plate fitting procedures ensured that thermal expansion joints could accommodate the dimensional changes that occurred during heating and cooling cycles. Fire tube arrangements were modified to promote more uniform heat distribution, reducing the localized hot spots that had contributed to accelerated corrosion in some areas of the original installations. Over the 20 years that followed, Carson's boiler fleet completed a service record that validated every aspect of his engineering philosophy. The units operated continuously through production cycles that included 2 major economic recessions, several facility expansions, and the transition from cotton textile production to the mixed manufacturing operations that characterized American industrial development in the early 1900s. Throughout this period, unscheduled maintenance remained minimal, while the structural integrity of the vessels showed remarkable stability. The final inspection conducted in 1915, when Green decided to modernize his entire steam plant, provided definitive proof of Carson's approach. Using the same measurement techniques that had been employed during original construction, inspectors found that the boiler shells retained an average wall thickness of 3/4 of an inch, a total corrosion loss of just 1/4 inch over 30 years of continuous service. The riveted joints remained tight, with less than 2% requiring recaulking during the entire service life. Most remarkably, the fire tube bundles showed minimal deterioration, with heat transfer efficiency remaining within 5% of original specifications. These results took on profound significance when compared to the performance of modern installations throughout American industry. Mills that had adopted thin-walled welded designs during the same period were experiencing service lives averaging 15 to 18 years, with many units requiring major overhauls within a decade of commissioning. The 3/8-inch wall thickness that characterized European practice typically lost 1/10 of an inch to corrosion within 15 years, leaving insufficient material for continued safe operation. Carson's generous corrosion allowance, initially criticized as wasteful over-engineering, had proven to be precisely the margin required for genuine long-term durability. The vindication extended beyond simple longevity to encompass the broader question of industrial engineering philosophy. Carson's approach had demonstrated that American manufacturing conditions demanded design solutions that prioritized reliability and maintainability over theoretical efficiency. The thick-walled, riveted construction that seemed primitive compared to sophisticated European welding techniques had survived operational stresses that destroyed more advanced designs. The modest operating pressures that had been dismissed as conservative had provided structural margins that proved essential for continuous industrial service. When Green's facility was finally modernized in 1915, 3 of Carson's original boilers were relocated to serve smaller industrial applications, where their conservative design and proven reliability continued to provide value. 2 units were eventually acquired by technical museums that recognized their historical significance as examples of American industrial engineering at its most practical and enduring. The museum installations allowed visitors to examine construction details that had been lost to modern manufacturing methods: hand-driven rivets, wrought iron plates, and fire tube arrangements that prioritized durability over efficiency. The final proof of Carson's legacy emerged decades later, when industrial archaeologists conducting surveys of 19th-century manufacturing equipment discovered that several of his boilers remained in operational condition more than a century after their original construction. Modern thickness measurements confirmed that structural margins remained adequate for continued service, while the riveted joints showed no evidence of the fatigue failures that had eliminated comparable welded designs decades earlier. A contemporary plant engineer examining one of these museum installations captured the essence of Carson's achievement when he ran a thickness gauge across the weathered iron plates and announced, "This is still at 0.72 of an inch. Remarkable." The numbers represented more than mere material durability. They embodied an engineering philosophy that had trusted time over speed, substance over sophistication, and American craftsmanship over theoretical optimization. When American workers built a boiler with 1-inch wrought iron plate, riveted joints, and modest pressure, they didn't just build an engine, they built something that trusted time, not just speed. That was American ingenuity.